I'd just like to echo Andreas' thanks to you all here today. Thanks also to the speakers, some of whom have travelled quite well to be here. So the general structure of this day is going to be 45-minute slots for a half-hour talk. So we really are trying to encourage people to get into long arguments with the speakers about whatever they care about. And we've tried very broadly speaking to group the talks into some kind of theme such that you might want to talk about both the talks after the second talk. So if people aren't causing a large argument after the first talk, we may move on to the second talk more quickly and then allow more time for discussion afterwards. So please feel free to ask wide-ranging, open-ended questions, provoke the speaker to rant about whatever their special interest is. And then at the end of the day, we may break a little early if we end up not using all the time. But we'll always start the session at the timetable time when the next session time rolls around. For the very last session, we're going to have one talk followed by a series of lightning talks from attendees. Currently, we have 3 of those talks registered. So if you have your own slides for WebAssembly from some other talk that you've given, and you'd like to Frankenstein together a last-minute lightning talk, please feel free to do that even at this late point, and I'll just be checking who's registered at the beginning of the last session. And then finally, we're going to end the full program of the workshop with a brief discussion on what people would like to see if we do this again in the future. This year, we've kind of done an oops all invited talks event to try and draw as many people to the workshop as possible and give a broad overview of what we think are some of the important problems people are thinking about with WebAssembly. But we'd like this to grow into a thing where everyone comes and shares their experience with WebAssembly. So for future workshops, for example, we'd be interested in hearing whether you'd like to do more submission-based talks, things like that. Something to think about for the last session. So without further ado, I'd like to introduce the good Wagner, one of the co-creators of WebAssembly, who's going to be talking about what is a WebAssembly component and why. You probably don't need this one.
All right. This is all right. This is how it works. Hello, everyone. Yeah, my name is Luke. I work at Fastly, and we're trying to answer the question: what is a WebAssembly component and why? And this is a modified version of a talk I gave last year at WASI, which was definitely an industry sort of focus, but hopefully it's like interesting to this group too. So first, before answering, asking what is a WebAssembly component, let's start with the question: what is WebAssembly and why? I appreciate most people here already kind of know that, but bear with me for just a second. So the boilerplate definition: WebAssembly is a binary instruction format for stacked instruction machines designed to support compilation target programming languages. And I think the operative phrase here is compilation target, meaning that we can take all a variety of source languages, and in addition to all the native instruction sets we can compile to, we can compile to WASM. And then given that WASM, exists in a browser or WASM engine, turn it into whatever actual native instruction set that we're running on. And why we do this, we get portability, determinism, if we want it, control flow integrity, and some cost sandboxing. And so using, what do we do with all these cool superpowers? So just kind of looking at the whole ecosystem, what are the popular use cases? Inside a browser, the 2 big clusters, that I see are, there's a whole bunch around porting a whole large code base that you've already written, especially this is like the famous way we started with mscripton. Big examples include Unity, AutoCAD, Photoshop, Earth, and Figma. And another emerging class of use cases is finding compute-intensive subtasks and punting them out from JavaScript to WASM. So, big examples being codecs, compression, inference, encryption, and filters. So that's in a browser, but we're also seeing a bunch of emerging use of WASM outside the browser. And trying to cluster these sorts of use cases, one whole cluster is around using WASM as a plugin into some existing physical system you've built. So you already have this whole system already working and you want to take some of your user's code and put it in there. So the last plugin you'll ever need is a little catchphrase that we've been using, throwing around. So there's the CDN use case, which is what Fastly does. We had a big CDN and we want to run users' code in our CDN to make the cache way more effective by controlling exactly what the cache key and what goes in when where. So that's what we do with it in Fastly, but also people are using WASM as user-defined functions in databases and in client apps and SaaS apps and Kubernetes sort of plugins and also streams like Kafkas and Red Pandas and such. And another clustered use case is using kind of the novel properties of WASM to explore alternative models of distributed computing around serverless or distributed actors or record and replay durable execution or edge computing, which is also a way to look at what we're doing in Fastly. So this is all a bunch of really cool stuff using WASM's unique powers, really neat things, and absolute value or absolute volume. A lot of people doing a lot of stuff, but
compared to like the size of the overall like software ecosystem, this is still kind of niche. You know, it's cool, but we want to see like just a ton more WASM. Like I think a lot of people here would like to see like everything by default be WASM. So the question to ask is like, well, what would it take to make WASM like more ubiquitous? What big new use cases could we unlock that would make, you know, WASM become far more ubiquitous? And I'd like to consider 4. So, number 1, today on many kind of compute execution platforms, you know, the client controls their application code, the platform vendor controls their, of course, their implementation and interface, but they also control the language runtime, and therefore the choice of language that you have when running on this platform. And the platform also controls the SDKs that you use in that language to access the platform. And this is both like a lot of work for the platform vendor. Now you have to maintain all these SDKs and worry about all these versions, which is like not actually your interest. And clients have a more limited set of choices of what languages they can bring to these platforms. So instead, you know, we could lean into WASM's language neutrality and linkable modules and say, yeah, of course, platform controls their implementation interface, and the client controls their application code, which they'll compile to WASM. But also, the client gets to choose and bring their own language toolchain, which will have a language runtime, which is a WASM module. And we don't want to have to like duplicate this into every client app, so let's factor this out and share this via some registry, so we're actually sharing the machine code of this language runtime between all the different applications. And the client also gets to bring a bindings generator, which will take that platform interface and synthesize an SDK for that language, also compiled to WASM. And now the client application is a linkage of all these 3 modules running on this platform. And this is not new. You know, if you look at what people are doing with OpenAPI and gRPC, it's this in a HTTP kind of microservice-y sort of setting. So it's not new, but in those cases, you know, that's fundamentally going through a network stack. So there's a decent amount of overhead in these existing approaches. So the wins from doing this in WASM is we let the client choose their language. The host does a whole lot less work. We're not forcing network round trips or forcing networking into the situation if we didn't want networking. And we're also giving a new opportunity for emerging languages to go into all these platforms without having to be like, you know, allowed in by the platforms. So I call this cluster of use cases SDKs for free. Number 2. Today, if I want to reuse code, there's, you know, tons of registries with lots of packages in each one, but they're relatively siloed from each other. It's harder to reuse code across these registries. Furthermore, when I build a single application using lots of packages from a single registry, they all kind of exist in the same, share the same global mutable state, which is an opportunity for them to have conflicts and cause bugs. And also they share the same privileges and capabilities for the whole application, which means if an attacker takes over one package upstream and I pull that in transitively in my application, that's, you know, what's called attack code has access to all the capabilities of the application, so they can like steal like my secrets, even if there's no reason for that particular package to have access to that particular capability. So this is like ambient authority. So to address these problems, we could lean into WASM's language neutrality and sandbox supports and say, let's have a single registry where it can have packages compiled from all sorts of different languages, compiled to WASM. And we put them in an app. Let's put each of these packages, give them their own separate memory and just the capabilities they need, so that way, you know, their attacks are, you know, somewhat limited in the extent. And the wins from doing this is we get to reuse code from other languages. We can mitigate supply chain attacks, and this helps again. Very good. All right. And again, we can help emerging languages, because now when you start a fresh language, you have access in your registry to all this code in all these different languages. So I call this, you know, use case secure polyglot packages. Number 3. Today, if I want to avoid, in software engineering what's called sometimes a big ball of mud architecture, you know, a popular kind of architecture you see a bunch of folks using, sometimes overusing, is microservices, where I put what could have been just different modules in wholly different services, and I have them talk to each other through HTTP, which is like a very big sledgehammer of modularity. They're really quite separate, which achieves that, but you know, at the cost of a significant complexity to deploy and manage and operate these things, and a decent amount of runtime overhead. And like, maybe that's what I want. This is part of like how I want to scale independently these services and do all this auto-scaling stuff. But if I don't actually want that independent scalability, this is like kind of overkill. So it's like a very popular thing, like in popular media, where somebody makes a blog post where they're like, look, just because you need like modularity doesn't mean you need to whip out a whole like microservices. This is like too much. Can we not just go back to like monolithic deployments and just be like, write modular code? And it's like, yeah, sure. Yeah, you can definitely do that. You could always have done that. But we are, and you know, have them just communicate with function calls. Just ye old, you know, function calls. It's much faster. Avoids a lot of that complexity. But we are now generally limiting ourselves to a single language or language family, depending on the VM. And they're less isolated because often these module features still have a fair amount of global shared state. So that's a thing I think people, why they go to the microservices, it's just like this very hard boundary of like, we are not sharing like anything except like, of course, the database, but that's a different story. So instead, we could lean into WASM's language neutrality, sandbox support, and linkable modules, and say, let's put our modules, compile them to separate WASM modules, and give them separate linear memories, because we can do that in WASM. And let's have them talk to each other through just function calls, because that's also a thing we can do in WASM. And by doing that, we combine the memory isolation and language choice of a microservice architecture with the efficient cross-module calls of a kind of a modular monolith. So I call this use case modularity without microservices. And lastly, number 4, today if I want to factor out code between different teams, I have like a large organization writing like tons of code. I have all these different teams, each maintaining their own service, let's say. And there's some shared code that's like, I just want to like factor out and share between all these teams around like authorization or RPC or observability. And it's like increasingly popular to have a platform engineering team in your organization that kind of maintains this stuff for the benefit of other teams in your organization. There's 2 popular options. The original one is you just develop a library that you embed into each one of these services. And that library often takes care of talking to like the network for you. But this is harder to update, because now when you make an update to the shared code, you have to redeploy every individual service. This amount of per language effort if you're using different languages in different services, and it can be a leakier abstraction. You can like get around a library somewhat easier. So instead, to avoid this stuff, another approach people use, which is called the sidecar proxy pattern, is you have your service talk through the network stack to the shared code, as a sidecar, sometimes container, and then that shared code then talks to the actual network for you, which like works and like kind of draws a harder line between them, but it comes at like significant measurable overhead. But it's still worth enough that people do this in mass. It's called like service meshes. So instead of doing all that, we could say let's lean into WASM's sandbox support and linkable modules. Say we'll have our different teams compile their code to different WASM modules. And then between them, there's this like interface. Sometimes it's called an internal developer platform, which is like the abstraction that all these teams like target that is maintained by the platform engineering team. And when we deploy this WASM module, we will link it with our shared module and have a composite module. And then that 2 linked modules is what we run on the underlying infrastructure platform, which supplies an actual WASM engine. The important thing is the infrastructure platform didn't really have to know about these higher levels. And this lets us combine the low overhead calls between modules of the kind of embedded shared library with the strong encapsulation between layers of the sidecar proxy approach. And this really starts to matter as soon as you have like multiple of these layers as they stack up, because this example shows 2, but it's actually, I think, going to be common to have like multiple of these layers. So, for starters, this business logic, let's say it's targeting POSIX. It's using traditional file system code because it was written a long time ago, or I'm using a library that uses file systems. Like that's very common. But internal developer platforms just tend not to actually have a file system. They don't give you NFS because like nobody wants that. They have like a key value store or a SQL database. So what do we need? We need a little virtual file system that kind of lets us have that abstraction of a file system in terms of what the actual underlying storage is. And so we can just link that together, deploy that to the internal developer platform, which links that with the original logic, and now we have 3 modules linked together running. And again, this infrastructure layer doesn't have to care. These are just higher layers. And let's do it one more time, because this internal developer platform in my company, let's say I'm building on some sort of platform as a service or function as a service. And of course, they're going to build their own features as a WASM module, let's say, that's linked to this thing. And now I have 4 modules linked together. And so you can see as the number of layers grow, you really want that low-cost, strong isolation. So you can you don't want subtle bugs that only show up in certain compositions, because those are going to be impossible to debug. On the other hand, you don't want stuff like, every time I add a layer, everything gets like exponentially slower. And this sounds like maybe pretty theoretical, but this is actually the leading use case that we want in Fastly. This is what we're starting to do now. We're building stuff at this level. We're doing work so we can build our own features as WASM modules that we can rapidly iterate and deploy without worrying about some wacky new feature taking down the whole system. So we want to isolate them to more rapidly develop features. And meanwhile, some of our users are working at this layer. They're building their platforms on top of Fastly. Their users don't know about Fastly. They're just deploying to their platform, which is on top of Fastly. So they're also excited about using components to be able to, again, build these abstractions at reasonable cost. So we call this use case virtual platform layering. So hopefully, some combination of those things are exciting enough that, can cause a lot more WASM usage. So the question is like, how do we actually do this? And I think fundamentally what we need to do is expand the scope of what we're building from a new compile targets for existing ecosystems where we're comparable to things like x86 or ARM or RISC, to a whole new ecosystem which is built around a new compile target, where instead we're comparable to things like containers, NPM, Nix, Maven, Helm, or Debian. So what makes an ecosystem? I don't have a general answer, but if you just like look at like containers and like, you know, say what's the pattern here, and that's sort of, and the things I just listed, you start with a standard-ish distributable formats. You have tools to build one of these things from sources. You have tools to deploy and run them, and tools to share and compose them. So if you take containers as an example, OCI has that standard-ish distributable format for what's an OCI image or container. We have tools like Docker build to build these things, tools like Docker run and Kubernetes to run and deploy these things, and tools like Docker push and Docker compose, share and compose these things. So the natural question is like, well, we have WASM. It's obviously a standard distributable format. Is that not enough? Can't we just use that? And obviously there's lots of existing WASM compilers and more every year. But the challenge is WASM mostly only supports shared memory linking. So if I have two WASM modules and I want to link them together, pretty much the only effective way, a practical way to do that is for them to share memory today. And you know, WASM GC somewhat improves upon the situation, but it's still shared low-level memory. It's still a very low-level feature, so it doesn't really address the problem either. And plus, lots of languages are just using linear memory. Instead, what we want, and so this is like operating system DLLs or shared objects, which is like, they're cool, they're useful, but that's not like your standard unit of distributable code. People don't like sling DLLs and combine them in these sort of ways I'm talking about. They're very fragile. They're fragile, man. So instead what we need is when I have multiple WASM modules and put them together, I want them to be able to have their own, maintain their own linear memories, and have some way to be able to copy values between them or pass handles to non-copyable resources between them, more like an operating system executable. So we could almost use WASM, but it's just a little too low level, quite intentionally, but it is too low level for this purpose. So the next question is, well, POSIX has been around for a while. It's a very popular abstraction level. Can we just take WASM, wrap it in POSIX, and have some sort of WASM executable concept? But let's speed run this, because you know POSIX executables have been around for a while. Is there an ecosystem of people like distributing POSIX executables in this way? No, because you never just want one. You want a group of executables and some configuration code and then some static assets and a little directory structure. And what's that unit? That's containers. So if we speed run this, we just end up with containers, but WASM's the instruction set, which is like totally fine. Like that's useful. It'll provide value to some people, but it's not going to like unlock just like all these totally new use cases, because containers have been around, they exist. Swapping out the instruction set won't change their fundamental physics. So we need something new, is our opinion. Something, of course, that it reuses existing WASM compilers, and that's something we're proposing is called a component. So finally, getting to the title of the talk, what is a component? So in one sentence, component is an emerging, standard, portable, lightweight, finely sandboxed, cross-language compositional module, which is like a super loaded sentence. So let me break that down word by word, going backwards. So I'll start by saying, so a component is a module by having imports, internal definitions, and exports. That's what it is at a 10,000-foot view, just like WASM. And imports are, I could import like functions, like this log function or this get function. And in general, imports are how we capture the I/O performed, the effects, and implementation dependencies, instead of having a fixed set of syscalls or a runtime global namespace. Internal definitions, these are just WASM modules that have like the meat of the actual code. This is just WASM modules with, and this is 99% of the bytes. And these WASM modules can call these imported functions. And components can also nest other components, so they're recursive by nature. And lastly, exports just, export imports and internal definitions, again, just like WASM. And exports are meant to capture host events and triggers and how generally client code calls into this component. Again, just like WASM. But instead of having a single fixed main function, which is kind of the thing everyone kind of gravitates towards naturally, which is sort of like saying everyone has exactly one export and has this fixed signature. Importantly, all interaction with the outside world goes through these component level imports and exports. There's not some sort of side door where the WASM gets to reach out and talk to WASM and other components or the system. It all is going through imports and exports, which means if you want to summarize it, if you would say viewing it as a black box, which its type, all you need to summarize it are what are the imports, names and types, and exports, names and types. And that's it. That's the entire, description of a component from the outside. And all you need to know to understand its interaction with the outside world. And this concept's very important. So in WIT, which is an IDL that we're building for the component model, we have a first-class concept for defining these things. And in theory, it's just a component type. But people tend to get confused if you say type in all these contexts, if you're not like inherently a typey person. So we were calling them profiles for a while, but now that term's taken for WASM, so we now call them worlds. So world is just like a synonym for type, but it's like the world you run in, which is nice. It's nice to say. So it's just a component type, and it defines the contract between guests and hosts, that are defining and running components. So a guest components target a world and when you target a world, you get to call the imports and implement the exports. And host runtimes duly, of course, support the world. They can by implementing the imports and calling the exports. And here, this example, I'm just importing only functions. We can also import groups of things, functions and abstract types, with an interface. So here I have a file system interface that I can import, or an HTTP handler interface that I can export. And then once I have interfaces, I can name them, give them standardized names, so that when we mean the same thing, we can say the same thing and then share code and actually achieve interoperability. So this is now, we can recontextualize WASI. Originally, WASI was just this fixed set of host calls. It's like, this is what the host gives you, exactly this set, monolithic. With this with the component model and this concept of interface, we can say WASI's job is to define a bunch of common interfaces for use in various combinations by many worlds. There's not one fixed WASI world. There's a collection of interfaces, and any particular component can import and export some subset of them, and any particular host can provide and call some subset of them. So we're trying to have multiple worlds here, because that's just going to recognize the heterogeneity of the overall compute ecosystem that WASM's being used in. There's not just one fixed world that everyone's running in. And if you try to do it, it just becomes very dynamically typed, because you can't really say anything, and everyone just hacks everything through modules, and it's like, it's a dev file. It's like, okay, sure, everything's a dev file. So we don't want to do that. So that's what it means for components to be a module. What does it mean to be a compositional module? Aren't all modules compositional? Isn't that what they are? Not really. And this is a subtle thing where people abuse this term a lot, but just to hand wave at it, I think we need fundamentally two things to be able to do things. One, we want to be able to compose components together and still produce a components. That is to say, components are closed under composition. We don't want to compose components and produce some new thing like, a container or a zip or a jar. No, it's still a component, which means you can do this again and again. And this was this key for this virtual platform layering, is we compose, produce a thing, and then compose again. So that's one thing we need to be able to do. And the other is, after composition, all the child interactions of the child components with the outside world are mediated by the parent in three ways. So a parent can forward its imports to the children and re-export its children's exports. A parent can link two children together as just an internal detail of the component. Or a parent can have its own core WASM that implements the imports of the child or calls the exports, allowing it to create a whole virtualized world that the child lives in. And because both these adapters on both sides can share the same linear memory, the parent has great power to just create its own complete virtualized execution environment that the child is running in, which we'll see in the next slide how that's useful. And these can be used in combinations. So I can have a parent that links two children together, adapts this import, adapts that export, re-exports that thing. So that's fundamentally the primitives that we have. So let's see how this is actually useful in an example. So in this example, let's say I start with some C code written 20 years ago that makes a thumbnail, and I want to turn this into an HTTP web service. So I'm going to start by compiling it with WASI SDK, which is a general tool for compiling C, C++, now to components. That will give me a component that's really POSIX shaped, right? This is old C code. It's going to assume there's a file system, and it's going to assume it's called WIA main. So we're going to get a component that imports and exports those things. But that's not really what I want to run, because I don't really have a file system in a lot of cases, and main's not great. So what I want is a component that has no imports, and it just exports this pure function. That give it a stream of input bytes, I'll give you a stream of output bytes. That component is a lot easier to reuse in a lot more contexts. So to perform that wrapping, I'm going to use a tool being developed in the Bytecode Alliance called WASI-virt. And the whole purpose of this tool is to virtualize WASI file systems and sockets and main in terms of not these things. So in this case, what it'll do is it'll take that incoming stream and store it to an internal virtualized file system, producing a file descriptor that you can read from by reading from the stream. And if you try to write to it, it'll say, no, it's a read-only file. And vice versa for the output stream. And it can then implement the file system using these streams that it's stored and store all these data structures in a linear memory in this parent component. So now I have a component that like is very reusable. Like if I want to thumbnailify a thing, this is the thing to use. So I can publish it to a registry of components, so it can be reused by other folks. So now I want to take this component and I want to turn it into some HTTP API. So I'm going to write, let's say, this in JavaScript. And I can componentize this JavaScript using another bytecode lines tool called componentize.js, and that will make a component that imports this thumbify function. And let's say I want to cache it, so I'm not recomputing the same thumbnail over and over. So I'm going to import a WASI key value cache, which is a interface that has lets you cache stuff in like a Redis or a memcache. And I'm going to export a WASI HTTP handler, which is how I receive a HTTP request and return an HTTP response. So now I have two components, but I want to link them together so I can have one thing I can run. So to do that, I use another bytecode alliance tool called WASM Compose. WASM Compose links these two together to make one parent component. And if we say, what world does this parent component target? It's a very minimal world that just imports a cache, which is very widely implementable, and exports an HTTP handler. So I can run this on all wide variety of cloud and edge and other sorts of server stuff. So that is the component I end up with. Very portable sort of component that I can run in production. But now let's say I want to locally test this. I want to run this on my local machine, which let's say doesn't know anything about HTTP or caches. It just knows about a traditional POSIX world because it's like running on my command line. It knows about file systems, sockets, and main. It's a traditional POSIX command view of the world. So to run this deployment components in this local testing scenario, I want to wrap it one more time with WASM Compose, and I'm going to do that by implementing this imported key value cache in terms of the file system, say by using this directory, some particular directory, as the cache. So there will be some mock testing components that was published in a registry that I can reuse. And then I can call into my HTTP handler by having an HTTP server component that speaks sockets, parses the HTTP protocol, and calls into my handler when it parses an HTTP request. So those again can be reusable components and as part of like a local testing sort of registry. So with this now I can test my deployment component exactly in terms of local stuff running on my local machine. And the kind of neat thing to notice about this is we have two totally unrelated implementations of WASI file system. There's the outer one, right, the one that's actually probably talking to the actual file system, but then we have this inner one way back that's been fully virtualized, right? So in a lot of systems, if you have a name, thing like file system, it's like a global symbol and like a global namespace, and everyone has to mean the same thing. Here, they're just parameters. They're just imports of a component, which, of course, I can link them separately because they're just parameters. But achieving this shift from saying there is no global namespace, there is no global whatever, syscalls, is kind of like the big part of the key that allows us to do these kind of complex compositions. And that's often what's a pain in practical software development today. So that's kind of an example of what it means to be compositional, and this is, I think, also key to this virtual platform layering, because each layer is going to have its own concept of what does a file system mean at this layer. So what it means to be cross-language, let's say I'm wanting to target this world that imports a log function, exports a run function. From JavaScript, I can just write a JavaScript import to import the import. So I import a log function, and I export a run function. And that's all I have to write in JavaScript. The type I see in the wit is list of string that gets turned into automatically by the bindings generator to a JavaScript array of JavaScript strings. So I can call join on them, makes a string, I pass that out to log. So I can pass this JavaScript file to componentize.js, which will generate a component that targets this world. And I can also do likewise for Python, writing a Python import. Python doesn't have exports, but the bindings generator can say, well, I'm going to look for a world that has the matching name, and it's the methods of this class will be the exports of the world. So that's where I can stick my run function. I can componentize that with another bytecode alliance tool called componentize.py, which will generate a component that targets that world. And lastly, with Rust code, I'll implement traits. I'll implement a run my world trait that has a function for the exports of the world, and I can call the imports via a extern crate generated by the bindings generator, so I can call the log function that way. I can componentize that with another bytecode alliance tool called cargo component that builds components in Rust. So here I'm showing lists and strings, but there's a whole bunch of value types. Characters, numbers, strings, lists, records, tuples, flags, variants, enums, options, and results. And these are all passed by copy between components. But sometimes you don't want to pass by copy. Either it's because it's not copyable or because it's large. So we have what we call resource types, which are really just abstract types that have a very clear concept of lifetime because we don't assume a global GC. And they're passed by handles instead. So just to show an example of what it looks like in my world, I could import buffer, which is a resource type that has these constructor and append functions. And they look like methods, so you're like, oh no, is this object-oriented? No, it's not object-oriented, it's just syntactic sugar. It turns into functions and abstract types, but with annotations that let bindings generators that are in object-oriented languages generate nice bindings. And once I have that type, I can use it in other function signatures. So to target this world, in JavaScript, I could import buffer, and it would just show up as a constructor function. So I could call a new buffer on it, and then call a method, the append method on this object that's wrapping the handle, and then I could return the handle. So that kind of gives like a sample of what it would look like to use these resource types from, say, JavaScript. So that's kind of a sample of the cross-language experience in components. So now let's look at like how does the sandboxing work? How does this work kind of like at a lower level? How does this work out? So if I have two components, they're going to have disjoint linear memories and tables. That's like the fundamental thing. There's this kind of, we call this the shared nothing model. And so just to work it through an example, let's say we have one component that implements a secret store interface. The secret store interface defines a secret resource type that like hides a secret, although it does allow you to expose it, and have a get function for looking up secrets by name. And then we have another component that imports that secret store interface. So let's say I implement this, the first component in Rust, and I don't have space to show what it would look like, but you're basically going to implement one trait for the secret store interface, and you're going to implement another trait for the secret resource type. And then JavaScript, let's say, can just import the get function, and then say I'm going to get and look up a key to get the secret. That's going to be an object that I can then call expose on. So that's like in this sample, let's see how the like control flow actually works like under the hood. So the call comes in to this run function. So I'm executing run. The engine's going to put that key string into linear memory, let's say at address 4. And now when I want to call get passing this key, I'm going to call get passing the address of the string in memory, which is address 4. But of course, Rust can't see this 4. Like, first of all, I can't see the JavaScript's linear memory, so something needs to happen. So the component model very precisely specifies how this key string will get copied into the Rust memory using the Rust memory's allocator, ultimately putting it some other address in Rust, which is like 8 here. So Rust will get the call to get, getting past the pointer 8 into its own linear memory. So now we're running in the Rust code. Rust code, let's say, makes an HTTP request to the database or the secret store or whatever, getting back the secret, which is, let's say, XYZ at address 1. So now we don't want to just return the string. We want to like wrap it up into a resource. So Rust code will be able to create a resource that encapsulates the address of this string in this resource. So that 1 is the representation of the resource, and now I have a handle of the resource in Rust's table at index 0. So if Rust wants to now return the secret resource to JavaScript, it says, okay, return the handle at index 0, and then the component model will specify that this handle gets moved into the callers table, which is JS here. So now the handle shows up in JS's table at index 0, and JS receives the index 0. So JS can't see that 1 that's hiding inside the resource. All it knows is that it can call the expose method, passing the index of the secret it wants to expose. So hopefully this kind of gives an example of how this is cross-component communication is a whole lot like inter-process communication, right? We're copying values between memories, and we're passing handles kind of like typed file descriptors. But we're using function calls here. We're not switching threads. We're not doing context switches, syscalls, all that stuff. There's no network stack. So it's on the same thread, in the same stack, in the same process, at least if we want it to be. So it's like processes, but lighter weight. Speaking of lightweights, components support the same lightweight execution model as WASM today, which is a part of the big reason why people are choosing WASM in all these outside the browser situations. So today, if you have some WASM and you have an execution platform, like a server execution platform, there's generally 2 phases you can do stuff in, the ahead of time phase and the runtime phase. So in like a server context, you would say the ahead of time phase is the part of the control plane, and the runtime phase is part of the data plane. So when I deploy this WASM, I'll AOT compile it to machine code, and then I'll distribute that machine code over the whole fleet. And now when a request comes in at runtime, the WASM runtime can cheaply create these little instances with fresh memories, all sharing the same machine code. And this is, today how we achieve our sub-process sandboxing and microsecond instantiation times, which is like, really pretty cool. So with components, we have now multiple nested components and modules inside that thing. But the compilation model doesn't really need to change. We just do this upfront fuse step where we take all those things and we fuse it together, synthesize some WASM that does the copying between memories, and we ultimately can make one WASM module using multi-memory. And now it can, just flow into the existing pipeline and compile it the same way. The only difference is now the instances have multiple memories inside of them, but it's basically the same. And so importantly, if you're familiar with previous component models that had big runtime services and other sorts of like heavyweightness to them, it's really not the case. This is like the same as WASM runs today, just more memories. But that's only one way to compile the components. The other way, which is really just an optimization, if you so choose to have it, is if this component is reusing modules or components in a registry, the platform can maintain an internal machine code cache of compiled versions of all these shared modules, so that when you deploy components, it figures out what can I reuse that's already in the cache, and so it can synthesize effectively a little internal linker script that says, combine these different linked blobs of code together to synthesize the components. So at runtime, this ends up looking kind of like DLL-like code sharing, between components, which is a lot good in a multi-tenant, highly multi-tenant situation. So yeah, that's how components can execute in a lightweight fashion like WASM today. Lastly, the standard portability story is, again, roughly the same as WASM. So the component model is being developed as a specification that's layered on top of the WebAssembly core specification, kind of like TCP is layered on top of IP in a sense. WebAssembly core, of course, has a formal spec, reference interpreter, and test suites, and we're working on the same with Lucy Amidon's doing a lot of the heavy lifting on the formal spec, reference interpreter, and we're getting a lot of help and advice from Amal and Andreas on this. So we're working to have something that is just as well defined as WebAssembly core. Of course, WebAssembly is in browsers today and is accessed by the rest of the browsers through the JS API. So we're also proposing to extend the JS API so it can also access in the same way components. Of course, this isn't implemented today, so we have a tool called JCO. JCO is like a kind of a general purpose component toolkit, Swiss Army knife thing that's NPM package. It has a transpile command that takes a component, which is a new binary format, and translates it into Core WASM 1.0 and JS glue code that can execute in browsers and Node today. So people are running components today in Node.js just using the polyfill technique, and that's how some people actually do their REPL iteration loop, is using JCO transpile. So even before, of course, the goal state is browsers implement it natively, but that'll take quite a long time. So, the polyfill works pretty well in the meantime. WASI proposals are now layered on top of the component model, so they can define their interfaces in a language agnostic way in terms of these component model interfaces. And when possible, JCO transpile will also offer, and is already starting to offer, different polyfills of various WASI interfaces in terms of web APIs. So, in a nutshell, that's what a component is. And I know we've been talking about this for kind of a long time, that some of y'all have been hearing about, but it's finally becoming real. We're weeks away from stamping the Preview 2 milestone complete. This has been implemented in WASM time and JCO transpile, and WASM Edge, which is a totally disjoint WASM engine, is also starting development. Preview 2 covers both the component model and a subset of WASI interfaces. And we're planning to have a vote in the next WASI standard subgroup meeting to say officially, we're not done, but this is Preview 2, and we're not going to change Preview 2 anymore. And the top line goal of this is stability and backwards compatibility, because if you've been following along with this, it's so many different tools all working together, and they're all changing slightly different times. It causes everything to be broken all the time, which frustrates everyone greatly. So we're trying to get out of that state. No, there's Preview 2. By default, that's what tools will emit, and run times will continue to support it, even as we move forward on future iterations. We also have built an automatic conversion that takes Preview 1 core modules and converts them into Preview 2 components. So you can, a whole bunch of existing Preview 1 stuff can just automatically run in Preview 2. And we're committing to build such a tool that goes from Preview 2 to our future iterations. So that way we can kind of migrate code as we make breaking changes. The Preview 2 feature list includes a first wave of languages. In particular, the Bytecode Alliance is working on Rust, JS, Python, Go, and C. A first wave of WASI proposals, namely file system sockets, command line interfaces, and HTTP. Preliminary support for WASI virtualization in the form of this WASI virt tool that I talked about. Preliminary support for component composition with this WASM compose tool. And more recently, this kind of new language that's basically like a linker script that lets you kind of wire up DAGs of instances and have like a lot of fine-grained control of exactly what component gets what, which is pretty useful. And lastly, experimental component registry tooling in the form of WARG and OCI component artifacts. That was last year. That's what we worked on. All last year is getting to this Preview 2 milestone. That's almost done, pretty much done. So this year it's all about improving the concurrency story. It's because Preview 2 does the best it can, but concurrency just ends up being unavoidably gnarly. As in the async interfaces, just to achieve the concurrency we need, like where we have lots of streams going in and out in all the directions, it just ends up making these interfaces like way more complex than you think they should be, and you have to end up writing manual glue code, which is the whole point of this stuff, is you don't have to have the manual glue code, you have bindings that are just like usable as is. Also, we have suboptimal streaming performance, and concurrency is not composable in two ways. One, if two components are doing concurrent stuff and one blocks, then they both get blocked. Why? Because they're not in separate threads. We don't want them to be in separate threads. We kind of like that they're on one thread, but we just need to figure out a stack switching story between components. Two, if you virtualize one async interface, you end up having to virtualize them all for subtle reasons. So in Preview 3, basically we want to solve these by just adding a native future and stream types directly to the component model and widths, which can make things just so much nicer. This can allow us to have ergonomic, language integrated automatic bindings, because futures would bind to promises, streams bind to readable streams, that sort of thing, in JavaScript at least. And efficient IOU ring friendly ABI for these streams, and composable concurrency. In particular, like in Preview 2, for complicated reasons, we have to have two interfaces for HTTP handlers, one for outgoing requests and one for incoming requests, and they fundamentally have different signatures, just for reasons that don't have time to go into, but that's the best we could do. There's two different interfaces. In the transition from 2 to 3, we'll be able to class them down to just one interface that just has the obvious signature. You have a function that takes a request, returns a response. I'm kind of slightly oversimplifying it, but roughly that. And what this means is that a component can import and export the same interface. The imported interface is how you make outgoing HTTP calls. The exported interface is how you receive incoming HTTP requests. And because it's the same interface on both sides, I can now compose two components directly together to achieve what's today called service chaining, where you have multiple services like chaining going through the network stack. Well, we can achieve that just using direct component linking, no network stack, which supports this whole modularity without microservices use case. Yeah. So that's what we're working on this year. If you see what's today in Preview 2 and you're like, ew, well, hopefully give us some time. We're working on that. So in conclusion, a component is an emerging, standard, portable, lightweight, finely sandboxed, cross-language compositional module. We want to use components to grow WASM ecosystem, providing SDKs for free, secure polyglot packages, modularity without microservices, and virtual platform layering. We are just about to release a stable Preview 2 developer release for widespread use. And if you're interested, get involved. The component model and WASI specifications are described in their appropriately named repos. There's a Bytecode Alliance meetings repo where you can find lots of open to anyone, not just official Bytecode Alliance members, meetings you can join on the implementation of these things. And there's a Bytecode Alliance Zulip chat that people can ask questions to helpful people on. And that's it. Thank you.
So I have a bunch of questions I could ask you about that, but first, does anyone else have any questions they'd like to ask?
I have a very simple, basic question. I am speaking into the microphone. Can you hear me? I need to eat the microphone or something. Yeah, so you said when you compose components together, you should get another component, and then you showed these worlds, and you were composing them using interfaces, which seem to be a different thing. What's the difference between an interface and a world?
Interfaces are these things we define as fragments. Components can import and export multiple interfaces. A world describes the totality of a single component's imports or exports.
Did you think about just conflating the two?
In practice, working out what people want to write when we're standardizing, you want to be able to standardize a thing that's a fragment, and that the usual term people use for that is interface, at least in this context. And in a separate context, you want to talk about classes of hosts and what they provide. And you want the thing, when you talk about the totality of what's provided, you want that to be structural, where it's kind of duck typey. It's like, well, I'm going to provide all these interfaces. You don't have to care what world I support explicitly, just that the interfaces you want are provided. And so worlds are kind of structurally typed. Interfaces, the name matters, because we're saying this is the name of this fragment of functionality. And so it ends up being in different developer toolings. I guess we're really very much in the space of providing developer tooling that's not too surprising or hard for people to use, and interfaces end up serving one role and worlds end up serving just a different sort of role in the developer experience.
Okay, I'm not entirely convinced, but
Please take your disagreement as long as it needs to in the break and so on. this is why we're here to talk about this. Anyone else have any questions?
So one of the key selling points, of course, is like cross-language, right? So, and this is great. But you also showed that you have all these tools, right? There's a lot of tool chain going on here. So if I was a language vendor, what's the amount of tooling that I would have to develop and provide to plug in my language into this whole ecosystem?
That's a great question. Yeah, it's so there's a lot of stuff you can reuse. Is I guess the point is you know, I think fundamentally your job as a language designer is emit core WASM, kind of like always. When you're talking about leaving your world, your components, you're talking about binding to WIT, so adding a WIT bindgen generator. So WIT bindgen factors out a lot of the common stuff, like parsing the WIT, resolving the types, giving you an internal AST that says, okay, here's the WIT. Bindgen what your specific language bindings for this. So you can add a WIT bindgen binding generator. There's already a number of generators, and you would just kind of add one more. So that's one thing. And then roughly at the top level, usually your language has like a standard like compiler driver, like cargo component, you know, cargo, or npm or whatever. Add like a subcommand that has various all-in-one tools for like build me a component, given a target world, and then some source code. You know, invoke the compiler, and then, you know, passing in the WIT and generating the bindings, do all the normal compilation like usual, and then we have another reusable tool called WIT component that takes the core WASM, wraps it up into a component with like the right, you know, types on the outside, and spits that out. So just a top-level driver to like wire up all these reusable tools together into a single-shot pipeline. But mostly it's like bindings generation and a little bit of, and also registry integration. As component registries become a thing, you'll want, our deal is that if you're using your language's native registry, like npm or crates, you want to make these component registries look like they are just in your registry, maybe in a little namespace, by bindgenning what the interfaces are in your language as if they were packages in your language. So there's some amount of registry integration you might also want to do to like pull in this component registries by default. So that's another sort of optional thing, but in theory, this reduces a lot the amount of work a language designer has to do in like mapping out the space of OMG, what do I even generate? Like write WASM that runs in a browser, but also not a browser, and like it's just like no, we've kind of said a lot of that's been figured out. Just like, you know, do some bindgen for these high-level types.
And the bindgen front-end stuff you mentioned that already exists, presumably written in Rust.
Presumably, you presume correctly.
Perhaps not the most pleasant language to write a compiler in.
Now there's a tool that says there's an executable. It happens to be implemented in Rust, but you don't have to care about that. That spits out a JSON file that has like all the process stuff that's like a lot closer to the AST. And the Go folks use that so that they do their bindgen in Go.
And the language you currently support from your end, from the Bytecode Alliance?
Yeah, it's these ones. Yeah, Rust, JS, Python, Go, and C have the most work, but .NET's having a lot of work more recently. I think Kotlin's poking around, has been doing stuff. I forget exactly where they are. And there's a bunch of other languages doing some amount of stuff, but you wouldn't say it's supported. PHP is poked around.
But some of them are like third-party contributions, I guess.
Yeah, that's right. The Go people are doing a lot of their own stuff right now. You know, Bytecode Alliance is heavily working on Rust, JS, and I think more recently there's been some C work, a little bit of Python work. Anyways, yeah.
Hi. Do I understand correctly that you are basically implementing a new type system of a higher level on top of the basic WASM type system? Because I saw some generic types like list of string or stream of string.
That's right, yeah.
So how is it specified, this type system, and how do you choose to,
Yeah, it's, so yeah, these are the value types, and some of those are type constructors, like list, and, you know, variants and stuff. Yeah, the component model defines, you know, a bunch of new AST of types and a binary encoding of them in a type section. It's okay. Like WASM, but just different set of types. In fact, a disjoint set of types. If you look at the binary format, the component defines an outer binary format that's like a container format that has a type section, imports and exports, just like Core WASM, but totally different sets of types. And then nested inside the binary, you can have just core modules exactly as defined by current Core WASM, just like inline in the byte stream. And so, yeah.
And so, so you specify how the types are represented in memory, but they're going to be represented differently depending on the language, right?
Yeah, I wouldn't say we specify how they're represented in memory. What we specify is during a cross-component function call, there'll be parameters and results that have high-level types. What we'll specify is the layout in WASM linear memory that we're going to expect when we're serializing out of your linear memory and copying into the other side's linear memory. So we have what's called the canonical ABI that says, if your target is like a list of string, pass me an I32. Here's exactly what we're going to do and expect it to be laid out in memory. And it's slightly configurable. So, and it could be more configurable over time because you get to specify these options as part of your component implementation details. So you can say, what string encoding do I want? Well, I want UTF-8, UTF-16, or Latin 1 plus UTF-16. And this is all just an encoding detail that's not observable to the outside world that configures how the spec parses linear memory to produce that abstract value, that, and the other side then does the opposite to say how it's written into their linear memory. So we don't specify a stable representation that's like persistent in memory. It's more of a copying serialization scheme.
So does the type definition syntax include things like whether the list of string can have strings that are actually shared, like the same value? Do you have a difference between pointer types and?
No, they're always semantically copied. In some case, only.
Yeah, but a single list of string could share the same substrings, right? Two of the string elements could point to the same string value.
Yeah.
The whole thing could still be copied, right?
Yeah, you're right, and that is actually allowed. If you have a list of strings, they can have pointers to the same shared memory, and that will work. It'll be a copy. It won't. They're just values, so you won't know that they're the same. But it's semantically, there's no sharing.
Yeah.
But
The sharing will be lost.
it will be lost on the other side. You're right. There's no deduping. Yeah.
So in your example where you're sending a string from JavaScript to Rust, what if the strings are pretty big? Is there a better way of doing it? You have to make a resource then, right? And pass a handle?
Yeah, in the preview 2 timeframe, your choices are copy the whole thing with values or pass a handle and then define an interface. In preview 3, you would pass a stream of char.
And can the copy type include resource handles?
Yeah, they can be nested, so you can have lists of tuples of, we have 2 kinds of handles at the moment, linear owns and borrows, which are scoped to the call. So you can have a list of owned handles to whatever.
Okay, thanks.
We have to move on to our next speaker for now, but please find Luke in the breaks and in future sessions, and he will never stop talking about components, so I promise you.
I promise you.